Okay, how do we handle any reactions in the mass balance? Let's look at that. So, if we have a reaction where a reactant A undergoes a reaction to form a product B, then the rate is equal to dC over dt is equal to minus kCn. So this is describing the rate of reaction, and where C is the rate of change, or C is the concentration, and dC dt is the rate of change of concentration, is equal to negative k C to the power n. Now what are these different variables that we just defined? Let's write them down. As I said, dC dt is rate of loss, of concentration, and this would be grams per meter cubed second. The units could be something like this. And then K is the rate constant, so if you have studied chemical kinetics, this is all a review of that. And this of course varies with n, and n is the reaction order. Which could be 0, 1, or 2, or it could technically even be a fraction, but typically we see these as 0 order, first order, or second order. And even amongst those, n is equal to 1 means it's the first order reaction, and his first order is very common. And in that case, dC over dt is equal to minus kc. And where do we use this, this reactions in mass balance? When we have radioactive decay, when we have reactions forming ozone, when we have carbon monoxide. So a lot of these situations we would use this kind of reaction terms in the mass balance. And so just to look at this one here, the dC dt equal to minus kc. So here a practical example could be the rate of leaving stadium is proportional to the number left inside. And so that's, you can all visualize that once the hockey game finishes, and then people are rushing to go out, and as the number of people left inside decreases, the rate of leaving the stadium also decreases. So that's something like that. Okay. And here the K would be the rate constant. The units of K, if you look carefully, units of K for first order decay are 1 per time, one per unit time, which could be equal to anything like 1 per minute, 1 per hour, and so forth. Now if we write a box model, okay, now that we learned this, if we do a box model with first order reaction, so now let's write down the equation again. M dot is equal to d Cv over dt is equal to m dot in minus m dot out plus reaction. Just using a short form for that. And this reaction, we write this as okay, everything has to be in the units of mass per unit time. So V times dc dt, volume V times dc dt, and then dc dt we just learned from here, V times minus kc if it's first order. So now if we look at what our equation is, it would be m dot equals qc in minus qc, I forgot to add the emission term here, plus E and minus kCV. And the C is the concentration inside the reactor or inside the box in this case. So this is inflow, this is outflow, this is emissions, and this is reaction. And this is mass accumulation. So now if we, so far what we have been doing is a steady state. In steady state, when we do steady state, the overall m dot is equal to 0. That means no mass accumulation. But let's do a non-steady state for a change. So this is whenever we do non-steady state, it's a little bit more involved mathematically. So m dot is equal to wait a second, m dot is equal to V, assuming the volume is constant, actually it is dCV dt, but volume is constant, so we can get the volume out of the differential. So V as dCV dt is equal to QCN minus QC plus E minus KCV. And now if we divide the whole equation by V, we get QCN over V minus QC over V plus E over V minus KC. So our interest is in C, so we can club. So QCN over V plus E over V, these will all be some constant value. So these are, you can say these are two constants, so this could be A and this could be B. So I'm saying QCN over V is equal to QCN over V plus E over V is equal to A, and Q over V plus K is equal to B. So we get dC over dt is equal to A minus BC. And now if this is now differential equations, dC over A minus BC is equal to dt, and we integrate the two, and you can look up the integration for this from your calculus class, but the integration of this would be minus 1 over B ln of A minus BC is equal to T plus, and just let's say, if I do uppercase A, which is this would be a constant of integration, and now we can solve for A by putting initial conditions. So we have the initial conditions are t is equal to 0 at time t is equal to 0. We have C is equal to C naught. And if I do that, let's see what that gives us. So now if I put this back in the equation, I get so What is that? What does that give us? So we get this is equal to T and from this we get A minus BC over A minus BC naught is equal to e to the power minus bt. And if we solve this further, or try to separate out c, we would get c is equal to minus or 1 over b a minus e to the power minus bt a minus bc naught so just trying to simplify it back. So I'm just trying to simplify this equation here. And so this is c, it's a function of t, so I can say c as a function of t is equal to c naught e to the power minus bt plus a over b 1 minus e to the power minus bt. And we know what our we know this so we know these values, what a and b are. A is equal to, yeah. And if you were to try to make a plot of this, say this is term 1 and this is term 2. Okay, let me color code it. If this is term 1 and this is term 2, so if we plot our x and y axis are x is t and y is concentration C. So for plot 1 would be C naught e to the power minus bt would be something like asymptotically decreasing exponential decrease. So that's one. For 2, if you look at it carefully, 2 would be, for the maximum value of 2, term 2 would go to a over b. So say if this is a over b, and so this is 1 and this is 2, and if we combine the two, and let's draw this in, if the combination, let's draw this as the total. So the combination would be Let's see, let me try to draw it again. Yeah, something like one, just draw it thicker. And this is 1 plus 2 in blue. So that's just to give you a graphical feel for this thing. Okay. Let's do an example now. So, okay, let's consider an example for mass balance with first order decay. So take a moment to read the problem, and then we will make a sketch or schematic of the problem. So there is concentration inside the vault, the volume of the vault, there is some ventilation, and because it says it's a contaminant free air, so Cin is equal to 0, and then V is equal to 160 meter cubed. C naught initial concentration is 29 milligram per meter cubed, and final concentration is 14 milligram per meter cubed. And we have to calculate the time it takes for this ventilation to bring the concentration from C naught to C. So let's write down our mass balance equation. Mass balance equation would be QCN minus QC plus E plus reaction. That's our general mass balance. But we don't have any emissions here, we don't have any reactions here, so it's pretty straightforward. And then actually we also don't have Cin as 0, so this is V dC dt is equal to minus QC. And if we just try to separate the variables, minus Q over V dt and we want to take this from C naught to C, 0 to T, so that's ln of C over C naught is equal to minus QTV. So this implies T is equal to minus V over Q ln C over C naught. And so T would be minus 160 meter cubed divided by 10 meter cube per minute, and ln of C is 14 divided by 29. If you plug that into your calculator, you would get minus 11.6. And what would be the units? Would be minutes. So that's one way to do it. And that's the way I prefer doing it. But the method 2, you could also just use the equation that we derived. we just derived an equation. Let's write that down again. The equation was Ct is equal to C naught e to the power minus Bt plus A over B 1 minus e to the power minus Bt. And what was A and B? A and B in this case were A is equal to QCin plus E over V, and B is equal to Q plus K, or Q over V plus K. Now you can clearly see there are no emissions, there is no Cin, so A is 0, and there is no K, so B is just Q over V. So if we plug this into this solution, actually this whole term goes to 0 because A is 0, and so we have Ct is equal to C naught e to the power minus Q over Vt, and T would be, so if you take natural log here, ln Ct over C naught is equal to minus Q over V times T. So this implies T is minus V over Q ln Ct over C naught, which is the same expression as we got from the previous method. Actually, 1 second. The time cannot be minus, so I made a mistake there. Actually, the negative and negative signs cancel out here. And so that's with method 2. I prefer method 1 because it's more generic. If conditions are slightly different, then this equation that we have here, that would not apply. So just always start with this equation, the mass balance equation, see what's given to you, what is not given to you, and then based on that you can start writing and solving for what's asked for. So I guess that's it for mass balance, and be assigning some homework problems so that you can get more practice doing these.